In this lesson, we want to evaluate the area under the graph of a function using what's known as rectangular approximation methods. So the goal of this lesson is to define and evaluate the area bounded by the graph of a function and the x-axis, like what we have shown down here. So in this graph we have some function defined by the black curve, and we would like to find the area bounded by the graph of the function, the x-axis, and between x equaling a and x equaling b. So we want to develop a method for finding this area. And then we're going to define what's known as the definite integral. So we need to start out with some definitions first before we can attempt to do this. So first we want to look at what's known as summation notation. So the sum of n numbers, a1, a2, a3 out to an, where we're adding all of them up, is denoted by this. Notice this is called summation notation right here. So the sum, that's what the capital sigma, the Greek letter sigma, is representing, the sum from I equaling 1 to n of a sub I. So the I right here is what we call an indexing variable, and this notation means that I varies from 1 to n in increments of 1. So I would be 1, 2, 3, 4 out to n. And so this notation here means just a1 plus a2 plus a3 all the way out to an. For example, if we want to look at evaluate the sum from I equaling 1 to 5 of I. So in this case the ai is I. Then the I goes from 1 to 5. So it would be 1 plus 2 plus 3 plus 4 plus 5, which if you evaluate that comes out to 15. Let's look at this one down here. If we want to look at the sum from I equaling 1 to 5 of I squared, so now the ai's are I squared, then that would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And evaluating each of these, we get this summation. And if you add all those up, you'll see that you get 55. So this is summation notation, and we'll be using this as we try to define the area underneath the graph of a function. Now here's a theorem for common summation formulas that we're going to be using. First of all, the sum from I equaling 1 to n of just a constant c, that's going to be n times c. And that's because what this notation means is we add c to itself n times. So this summation notation here just means c plus c plus c plus c n times. And so of course that's going to be n times c. Now here's one that's not obvious at all. The summation from I equaling 1 to n of I is n times n plus 1 over 2. So in other words, all we have to do is put the upper limit n into this formula right here, and we'll be able to obtain the sum of 1 plus 2 plus 3 plus 4 all the way out to n. So that's what this formula right here is telling us. So written differently, it's telling us that 1 plus 2 plus 3 plus 4 all the way out to wherever we end at, n, the number n, is just n times n plus 1 divided by 2. And then we have two other formulas here that we're going to use. The sum from 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. And the sum from 1 to n of I cubed is n squared times n plus 1 squared divided by 4. And then we have another formula that we'll use as we're evaluating areas. The sum from 1 to n of c times ai. You can actually move this c outside in front of the summation as long as it does not depend on I. So you can move the c out in front like we have written right here. And that's whenever the c does not depend on the indexing variable I. You can do that. In other words, c is just a constant. It never changes. So for example, let's verify that the sum from I equaling 1 to 5 of I squared is 55 using part 3 up here. Now you can just add these numbers up, of course, 1 plus 4 plus 9 plus 16 plus 25, and verify that you get 55. But let's use this formula right here and verify that that's an alternative way of getting 55, an easier way in fact. So using this formula right here, the n is 5. That's what our n is. So we just plug that into the formula. 5 times 5 plus 1 times 2 times 5 plus 1 divided by 6. And notice we have some cancellation here. 5 plus 1, that cancels. That's 6. That cancels with this one. And we end up with 5 times 2 times 5 plus 1, that's 11, and we get 55. And so that verifies this formula for this particular value of n. Let's evaluate the sum from 1 to 5 of 3 times I squared. Well, by part 5 up here, we can just move that 3 outside of the summation. Since it doesn't depend on I, it's a constant, so this is going to be 3 times the summation from 1 to 5 of I squared. Notice sometimes I won't write I equals 1 when it's understood what the indexing variable is. And now we already know that this is 55, and so this is just going to equal 3 times 55, which is 165. So those are some theorems, some formulas that we'll be using. Now let's take a look at an example where we approximate the area under the graph of some function. So we're going to consider the function f of x equals x squared for x between 1 and 3. And what we want to do is we want to approximate the area under the graph of that function. So here's the way we're going to do it. We're first going to partition the interval from 1 to 3 into n subintervals. Each subinterval will be of width 3 minus 1 divided by n, or 2 divided by n, as shown below. So let's take, here's what we mean down here. Here's what we're going to do. So in this graph down here, you see the blue curve, that's our function, y equals x squared. And we want to approximate the area from 1 to 3. That's underneath the graph of the curve. So right here's our curve. So we want to approximate the area under the green portion of the curve that I have sketched from 1 out to 3. Now what we're going to do is we're going to break the interval from 1 to 3 into n subintervals. Now in this picture we have it broken into 4 subintervals. You see n is equal to 4 in this case. And we're going to add up the area of these rectangles right here. Now notice that the width of each rectangle down here, that distance is what we call our delta x. And in this particular picture, that delta x is equal to 3 minus 1 divided by the number of subintervals we have, which is 4 in this case, and we get 1/2. So that's the width of each subinterval. And then we're going to add up the area of each rectangle. Notice also that for the first rectangle, this point right here, that is our point 1 plus delta x. 1 plus the width of our first rectangle. The second point here, that is 1 plus 2 delta x's. The third point is 1 plus 3 delta x, and so on. So now let's come up with a formula for the area of these rectangles. So here's a formula that we're going to start with for the area of the rectangles being added up. First of all, the area of this first rectangle right here, that's going to be f of 1 plus delta x times delta x. Notice this point right here, as we just mentioned, that is 1 plus delta x. So the height of the rectangle, this distance right here, that is f of 1 plus delta x, because that point is on our curve, and the height is f of 1 plus delta x. So this is our height right here. And then the width of the rectangle, that is delta x. So this is the width. So when we multiply these together, we get the area of the first rectangle. The area of the second rectangle, this one, well, that point right there, that is 1 plus 2 delta x's. And so the height, this distance right here, that's f of 1 plus 2 delta x, so that is this value. And then the width is delta x again. And so the area of this rectangle is this quantity. And then we just keep doing this. Notice how we increment the delta x right here. We have 1 delta x, and then 2 delta x's, and then we'll have 3 right here, f of 1 plus 3 delta x times delta x. So this quantity right here would be the area of the third rectangle right here, and so on, all the way to the end, all the way to the very last rectangle. Now what we want to do is simplify this quantity and evaluate it and see what happens as we let the value n go to infinity. Now take a look at this graph up here and notice what happens as we let n go to infinity in this graph. Notice as we let n go to infinity, the area of all those rectangles, if we add them up, is approaching the area, the true area underneath the graph of our function. Notice how accurate it's becoming. Let me do that one more time. So we start out with large blocky areas, and as we let n go to infinity, the area of the rectangles is approaching from above the area underneath the graph of the curve. And so we're going to let n go to infinity, and we're going to obtain a number, and that number is what we're going to call the area under the graph of the function. And as we'll see for this particular example, this value, as n goes to infinity, will eventually approach 8.6, repeating like that. That will be our area, as we'll see. So let's continue down here. So we see that this is how we can represent our area. So this quantity right here represents the sum of the area of the rectangles. And this is just using summation notation right here. So notice how we have an I in front of the delta x. I goes from 1 to n. So we have, notice up here using this formula, 1 plus 1 times delta x. And then we have 2 delta x's here, and then 3 delta x's, and all the way to n delta x's. So we just represent that with an indexing variable I, going from 1 to n. Now, the delta x is the distance, the length of our interval, which in this case is 3 minus 1, divided by the number of partitions that we have. So this is 2 over n in this case. So we put 2 over n in place of the delta x, and we obtain this. Now we have to simplify the f of 1 plus I times 2 over n. Well, remember, f of x is x squared for this particular function. And so f of this quantity right here will be, that's our x, and so we just have to square it. So here it is. So this quantity right here, that is f of 1 plus I times 2 over n. And we multiply that by 2 over n. So this carries down. Now we're going to FOIL this out. Now when we FOIL it out, this quantity right here, when we FOIL it out using our FOIL formula, we get this. Notice this 1 comes from 1 squared. 4 over ni comes from 1 times I times 2 over n plus I times 2 over n times 1. So that's going to give us our 2ab is this quantity right here. That's our 2ab. And then I times 2 over n times I times 2 over n gives us 4n squared, 4 divided by n squared times I squared. And then we still have our 2 over n right here coming down. Now we distribute the 2 over n into each term. So this will distribute here, and here, and here. And we'll rearrange so the powers of I go from high to low. So we get 8 over n cubed, I squared. That's 2 over n times this first term right here. That gives us this. And then 8 over n squared times I. That comes from this term right here, being multiplied by 2 over n. And then 1 times 2 over n is 2 over n. So here we've boiled it down to this now. And now we're going to break this apart and evaluate it using the previous theorem that we looked at. So here's how this simplifies. And so what we're doing here is we simply distributed the summation to this term, and this term, and this term individually. You can do that because everything's being added. So we have the summation 8 over n cubed I squared plus this and this. Now, these are constants that do not depend on I. This is also a constant right here. Think of that as being multiplied by 1. So each of these can be moved out in front of their respective summations, and you end up with this. So notice in the first term we moved 8 over n cubed out in front. So right here it is. Here we moved 8 over n squared out in front. And here we moved the 2 over n out in front, and what was left was a 1 right here. Now we can use our formulas for the sum of the squares of the first n integers and the sum of the first n integers right here, and the sum of a constant. So remember, if you look back at the theorem that we had looked at, this quantity right here is going to be n times n plus 1 times 2n plus 1 over 6. So this gives us this term right here. The sum from 1 to n of I, that gives us n times n plus 1 over 2. And the sum of the number 1 from 1 to n just gives us n. You can easily see that one because you're adding up 1 to itself n times. 1 plus 1 plus 1 n times just gives you n. Now we can simplify this a little bit. Notice this n cancels right here. And we end up with our final answer right here. It doesn't look very pretty, but we'll work with it. So that's our final answer for the area of all of those rectangles being added up. And now we're going to denote this as follows. We denote this as capital S of n, and we call that an upper approximating sum. We'll talk about that in a second. Notice that it's equal to, this is what we found it to be, right here. And we can simplify this a little bit by multiplying out, foiling out this term right here, n times n plus 1 times 2n plus 1. That gives us 2n cubed plus 3n squared plus n. And n times n plus 1 just gives us n squared plus n right here. Now notice, this is the important thing to note. If we take the limit of this quantity as n goes to infinity, notice what we get. As n goes to infinity, 8/6, that doesn't change. So right there's our 8/6. This quantity right here, this rational function, notice the degree of the top is the same as the degree of the bottom. So as n goes to infinity, the limit of this is going to be the quotient of the leading coefficients. And the leading coefficients are 2 over 1. 1 times n cubed. So this quantity right here is approaching 2 as n goes to infinity. The 4, that stays 4. This quantity right here, once again, you've got a rational function. Degree of the top is the same as the bottom. So as n goes to infinity, this quantity is approaching 1. So that's approaching 1. So I have a 4 times 1 right here. We'll just say that's approaching 1. And then the 2 just hangs around. So right there it is right here. So in the limit, as n goes to infinity, this quantity up here is approaching 26 over 3. Notice that you get that just by adding up 8/6 times 2 plus 4 plus 2. You can verify that is 26 over 3, which is 8.67. And that's what we define our area to be. Now, just some notation here. In this case, we call capital S of n, what we found, an upper approximating sum. And that's because the function f of x for each rectangle was evaluated where it has a maximum value on each subinterval. We'll take a look back at that in a second. Now in this case, this also happens to be called the right rectangular approximation method because the function f of x was evaluated at the right endpoint of each subinterval. And so we may also denote this as follows. It may also be denoted like this. So instead of using the terminology capital S of n, we might use RAM. That represents, or that is the acronym for right rectangular approximation method. N is the number of partitions that we have, and our function f of x. And we found that it was this quantity right here. And then we took the limit as n goes to infinity, and we found our answer to be 26 over 3, or 8.6, repeating. Now, just to convince you about this upper approximating terminology, let's look back at the graph that we had earlier. So here's what we're talking about, the maximum value of the function over each subinterval. Notice for the first rectangle right here, to evaluate the area, the height is evaluated where the function, right there's our function, has its maximum value. Notice since this function is increasing, it has its maximum value at the right-hand endpoint of our first subinterval. So that's why this is called the right rectangular approximation method. And it also, because our function is increasing, just so happens to be our upper approximating sum, because that's where our function has its maximum at the right-hand endpoint of the subinterval. And the same thing for the second rectangle here. You see we evaluate its height for the second subinterval, we evaluate the height of this rectangle at the right-hand endpoint, and that's where our function has a maximum. And before we leave this graphic that we have here, just notice how the areas, this number right here, that 13, represents the area of the rectangles. Notice how this number approaches the true area, 8.67, or 26/3. Notice how it approaches this number from above. That means that this number decreases towards 26/3 as n approaches infinity. Just watching this, as n increases, notice how those numbers are decreasing, the areas are decreasing towards 8.67. And if we let n get larger than 100, if our graphic would let us do that, you would see this number getting closer and closer to 8.6 repeating. Now, we could have also approximated the area by evaluating the height of each rectangle at the left-hand endpoint of each subinterval. Now this would be where our function f of x actually has a minimum value on each subinterval. And let's see what we would get if we would do that. So here we have a graphic of what would happen in that case. So notice now that each rectangle, we're evaluating the height of the rectangles at the left-hand endpoint of each subinterval. So now our areas are under approximating the true area under the graph of the function. And notice that as we let n go to infinity, these values, which are the area of the gray region, the area of the rectangles, will approach 26/3, or 8.67, from below. So just to see that, watch as we let n get larger, those numbers, they're approaching 8.67 from below. Do that one more time. Notice how the area of the rectangles are filling up the area underneath the graph of the curve. And they will be approaching 8.67. If we could let this number get larger and larger, we would see that. Now let's do this analytically and see that in the limit as n goes to infinity, we will still get 8.67. So now, if we look at our formula for the area of those rectangles, so this quantity right here, that represents the area of our first rectangle right here. Notice that we're looking at f of 1, that's the height, that's this distance right here, that's the height of that first rectangle, times the width, delta x. And so this gives us the area of the first rectangle. The second rectangle, notice we evaluate f of 1 plus delta x, that's this point right here. That point right there is 1 plus delta x. When we evaluate f of that quantity, we get this distance. And then we multiply by delta x, and that gives us the area of our second rectangle. So that's the area of the second rectangle, and so on. This quantity right here that would be the area of our third rectangle. Notice f of 1 plus 2 delta x would give us this distance times the width, and that gives us the area of the third rectangle, and so on. Now notice that we only go out to f of 1 plus n minus 1 times delta x. So we have 1, 2, 3, 4 rectangles here, but we would only go out to this last point right there. That would be 1 plus 3 delta x. So notice, even though we have 1, 2, 3, 4 rectangles, we only go out to n minus 1. So this quantity right here would represent the height of our very last rectangle. So we only go to n minus 1. Now let's turn this into a summation formula, and this will look exactly like the summation formula we had before, except instead of going from, for our previous summation formula, we went from 1 to n. Well, instead of going from 1 to n, you notice we're going to go from 0 to n minus 1. And if you look at this formula right here, you can see that. You see right here that f of 1, that is the same as 1 plus 0 times delta x. So my indexing variable starts at 0, and it goes to n minus 1 times delta x. And so we can represent this quantity using this summation notation right here. And now we replace the delta x with 2 over n. That doesn't change. We have n subintervals, and so the width of each subinterval is going to be 3 minus 1 divided by how many we have. So that's 2 over n. That's the width of each subinterval up here. So that would be this distance right here. That would be delta x, or 2 over n. We put that in place of the delta x, and now we simplify this. Remember, once again, the f of x, that's x squared. So right here is f of this quantity right down here. Notice we just square it. And now we're going to simplify this. So let me scroll down. So we're sitting right here at this step. Now we just have to FOIL this out. We're going to simplify this by FOILing it out, and we get this. This is the exact same procedure we went through before. It's only that our indexing variable is going from 0 to n minus 1 instead of 1 to n. Everything else remains the same. And then we get down to this. Once we distribute the 2 over n inside, we get down to this. And then we break our summation apart like this. And we pull out the 8 over n cubed in front of the summation, and the 8 over n squared gets pulled out, and the 2 over n gets pulled out in front, just like we have down here. And now, on each of these formulas right here, we can use on each of these terms, we can use our formula. So this quantity is, now we have to be careful, it's going to be n minus 1. You see our upper limit here now. That's n minus 1. So if you remember, our formula for the sum of the squares of the integers was n times n plus 1 times 2n plus 1 over 6. But now we're putting in n minus 1 in for the n here and here and here, because we're only going to n minus 1. So when we do that, we get n minus 1 times n times 2 times n minus 1 plus 1 over 6 times 8 over n cubed. And for this formula right here, you remember the formula for the sum of the first n integers was n times n plus 1 over 6. Well, now we need to put n minus 1 in here for n. And we get n minus 1 times n right here. And then the sum from 0 to n minus 1 of the number 1, that's actually still going to be n. Because I goes from 0 to n minus 1, you're still adding 1 to itself n times, because you're starting at 0. And so you still get n there. Now those n's cancel, and we end up with this. So we end up with this formula down here. And let's see what happens as we let n go to infinity. Let's just make sure that we still get 8.67. So let me scroll down here. Now we're going to denote this quantity right here that we found as little s of n. We're going to call that a lower approximating sum, because the rectangles were under approximating the area of the graph, and we found it to be this quantity right here. Now let's factor out, if we were to multiply this out, the numerator right here, we would see that we would get 2n cubed plus some lower order terms. We're only really interested in the highest order term when we take the limit as n goes to infinity. And then, well, this one's easy. When we multiply this out, we just get n squared minus n, this part right here. Now, if we take the limit of this quantity as n goes to infinity, notice that we still have our 8/6. Right, so that's right down here, 8/6. This term right here is approaching 2. Notice we have 2n cubed over n cubed. So the degree of the top is the same as the bottom. So the quotient of the leading coefficients, 2 and 1. So this is approaching 2 as n goes to infinity. This term right here, degree of the top is the same as the bottom. Leading coefficients are both 1. So this is approaching 1. And the 2 just stays 2. So when the limit as n goes to infinity, we end up with 8/6 times 2 times 4 times 1 plus 2, and when you add all of this up, you still get 26/3, or 8.67. And that's the same value that we got for the upper approximating sum. Now let's take note of that notation down here. Now in this case, we call little s of n the lower approximating sum, and that was because f of x was evaluated at where it has a minimum value on each subinterval. And since the function f of x had its minimum value at the left-hand endpoint of each subinterval, we will also call this the left rectangular approximation method, and we'll denote it like this. So notice that we'll use the notation LRAM, meaning left rectangular approximation method, for the function f. And in this case, we found it to be this quantity right here. And when we took the limit as n goes to infinity, we found it to be 26/3, or 8.67, which was the same as what we had found for the right rectangular approximation method, or the upper approximating sum. And just to recall the graphic that we had for that, notice once again here, on each subinterval, we're evaluating the function, the height of each rectangle where the function has a minimum, and that happens to be at the left-hand endpoint of the first interval, left-hand endpoint of the second interval, left-hand endpoint of the third interval, and so on. And that's because our function was increasing. If our function were decreasing, then the left rectangular approximation method would actually correspond to the upper approximating sum, and the right rectangular approximation method would actually correspond to the lower approximating sum. And we'll take note of that and write that down in an upcoming slide. Now let's take a look at a definition here. So this is our definition for upper and lower approximating sums. So we let a function f of x be continuous over an interval ab, and we partition the interval ab into n subintervals of length delta x, and that's going to be b minus a over n, as we saw previously. On each subinterval, xi minus 1 to xi, we let f of little mi be the absolute minimum of the function f over that subinterval, and f capital Mi be the absolute maximum of f over the subinterval. We then define the upper approximating sum, denoted like this with a capital S, to be the summation from I equaling 1 to n of our maximum values of the function over each subinterval times delta x, and our lower approximating sums, denoted like this, to be the summation of the minimum value of our functions over each subinterval times delta x. And also notice that the subintervals, the xi's, are actually a plus I times delta x. That's what the xi is, and the xi minus 1, that would be a plus I minus 1 times delta x. And also notice we have this relationship. The lower approximating sum is always going to be less than or equal to the upper approximating sum, naturally, because the upper approximating sum, you're using maximum values for the function, and lower approximating sum, you're using the minimum values for the function. So that's our definition for upper and lower approximating sums. Let's now take a look at this definition. So here's our definition for RRAM and LRAM. So if we're given a function f of x defined over an interval ab, we define RRAM to be this quantity. So here we're evaluating the height of each rectangle at the right-hand endpoint. That's what this is doing because our index goes from 1 to n. And we define LRAM to be, it looks exactly the same, except the index goes from 0 to n minus 1. Notice that difference. That, by going from 0 to n minus 1, you're evaluating the height of each rectangle at the left-hand endpoint of each subinterval. And also the delta x is b minus a over n for both. Now let's take a look at the relationship between LRAM, RRAM, and the upper and lower approximating sums. As we hinted at before, if our function f of x is increasing, then RRAM is the same as the upper approximating sum, and LRAM is the same as the lower approximating sum. So graphically, to understand that, if you have an increasing function and you take a subinterval, if you evaluate the height of the rectangle at the right-hand endpoint, then you're going to get the area of this, and notice that the right endpoint is where our function has its maximum value over this subinterval. So you see RRAM corresponds to our upper approximating sum, and if you evaluate the height of the rectangle at using the left-hand endpoint, you'll get the area of this rectangle. And notice that the left-hand endpoint is where our function has a minimum value over this interval, and so we see LRAM would correspond to the lower approximating sum. If our function is decreasing, then our graph changes to something like this. And notice that if we pick a subinterval right here, notice that at the left-hand endpoint is where our function has a maximum value, so LRAM would correspond to an upper approximating sum. And at the right-hand endpoint, our function has a minimum over this interval, and so RRAM would correspond to the lower approximating sum. So the relationships reverse, whether the function is increasing or decreasing. If our function is both increasing and decreasing over a subinterval, then there is no direct relationship between RRAM, LRAM, and the upper and lower approximating sums. Now let's consider this theorem. This is a very important theorem. If we let f of x be a continuous function over an interval ab, and we partition ab into n subintervals of equal length, like we've done before, and we let ci be any value in the ith subinterval, then the following results hold. The lower approximating sum is going to be less than or equal to the summation of the function evaluated at the ci values times delta x. And what each of these values represent is the area of a rectangle, and that's going to be less than or equal to your upper approximating sum. And the second part here states that in the limit as n goes to infinity, your lower approximating sums and your limit as n goes to infinity of the upper approximating sums exist and are equal, and so that forces, by the squeeze theorem, the middle term here in the limit as n goes to infinity to equal that value as well. Now, graphically, what's going on in number 1 is the following. If we have a function, let's just say it looks like this, and we take a subinterval and we evaluate the area of the rectangles. Now let's say that point right there is our point C. We'll just call it C or CI. Now if you evaluate the area of the rectangle using an upper approximating sum, you're going to get a picture that looks like this. Okay, so the blue rectangle would be the area from an upper approximating sum. If you evaluated a lower approximating sum, you would get this, the area underneath the area of the rectangle under the red line would be your lower approximating sum term. Blue is your upper. And then the one in the middle would be this. If we evaluate the function f of ci and we take the height of the area of the rectangle under the yellow curve, that would be representative of the middle term right here in the summation. And so you see the area under the red line is less than the area under the yellow line, and that's less than the area under the blue line. So that's where this inequality is coming from. And in the limit as n goes to infinity, we're saying that all of these quantities happen to be the same. And that's exactly what we saw in our very first example, if you recall, when we saw that the upper approximating sum approached 26 over 3 as n goes to infinity, and the lower approximating sum also approached 26 over 3, or 8.67. And so the term in the middle would have to also approach 26 over 3 as n goes to infinity. And so this is a very important result to note. What it's saying basically is that it doesn't matter where you evaluate the height of your rectangles for a continuous function. In the limit as n goes to infinity, you will get the same value. And so we have this definition then resulting from this. Here we have our definition for the definite integral. We use this notation. This is called the definite integral to represent the limiting value of our approximating sums. And it's important to note that from the previous theorem, for our approximating sums, it does not matter where we pick the CI values in each subinterval. And remember, the f of CI represents the height of our rectangles, and then when we multiply by delta x, this quantity represents the area of a rectangle. And it doesn't matter where we pick the CI values in each subinterval, in the limit as n goes to infinity, this quantity will approach a common value. And that is as long as our function is a continuous function. And we denote that number using this notation. And let's note that in the example that we looked at previously, we found that the definite integral from 1 to 3 of x squared is 26 over 3. Now, for those of you who've already had calculus, let me take note that you might be used to evaluating this by taking the antiderivative of x squared and evaluating it at 3 and at 1 and subtracting the two numbers, and you will get 26 over 3. So for those of you who haven't seen this yet, this is a little foreshadowing of what's to come. Notice that if we do this, if we evaluate the antiderivative of x squared, that would be x cubed divided by 3. And we evaluate it at 3 and at 1, and we subtract those two numbers. Let's denote it like this. So if we put 3 in for x, we get 27 over 3. And if we put 1 in for x, we get 1 over 3. And if we subtract those two numbers, notice that we get 26 over 3, which is the same as what we found by evaluating the limit of our right and left rectangular approximation methods. Is this a coincidence? No. This is actually what the fundamental theorem of calculus states. The fundamental theorem of calculus makes the statement that the definite integral from a to b of a function f of x dx is the antiderivative of little f evaluated from a to b, meaning you take the antiderivative, put the b in for the x, put the a in, and subtract those two numbers. And this, once again, is where capital F is the antiderivative for little f. This is our fundamental theorem of calculus that we will be getting to in another lesson. And before we leave this slide, let's note one other thing about the limit notation that we have above. Whenever you see this limit notation, notice how in the limit as n goes to infinity, we think of this summation as turning into the integral from a to b, as we have over here. The delta x we think of as turning into the dx in the limit as n goes to infinity, and what's in here, we think of the ci as just turning into an x, and we get f of x in here. So anytime you see something like this, you'll think of it turning into a definite integral. And this is a very common theme in mathematics and many fields of science, like physics in particular. And that concludes this introduction to the definite integral.